All right. This is lecture 30. Today we're going to be talking about sequences and series. So when we talk about sequences, we're talking about patterns. We're talking about a series of numbers that are either going to increase by a number, we call it D, and that number is going to be the common difference. Now, when we add a number each time, that's called an arithmetic sequence. But when we multiply by a number each time, which we call R, that means that it's a geometric sequence. So there are two different types of sequences. And so we have two different types of series when we get to series. Okay? So let's start off with the definition of series. A series is the sum of all terms in a sequence. The sum of all terms in a sequence. Now, I was talking earlier about how sequences can be finite and how they can be infinite. Well, an infinite series never ends, but a finite series is going to terminate at some number. So down here, I have a problem. It's adding up every single number from 1 to 100. And back in the 1780s, there was this guy named Carl Gauss. He was living in Germany at the time. And at the time of his birth, Germany didn't even exist yet as a country. He actually lived in a place called Lower Saxony. But this was apparently a math whiz kid. He could do math really easily. One time, his math teacher gave every single student an assignment to add up every single number from 1 to 100, at least the whole numbers, right? And usually this takes a good amount of time, maybe every single other student took an hour, but Gauss only took about a minute. He realized that there was a pattern that he could exploit that would allow him to get to the answer sooner. And apparently every single kid had their own chalkboard. And so Gauss wrote down a number and he put it on his chalkboard. He laid it on the teacher's desk and he said that he was done. And the number on the chalkboard was 5050. 5050. So how did he get to this number that quickly? Well, what he did was he actually grouped the numbers together, the ones that would go together. So, for example, he would put the 1 with the 100. So he's putting the first number with the last number just to see what he would get. So 1 plus 100, that would give him 101. So he puts these two numbers together. And then what he does is he puts the next two pairs of numbers together, right? He puts the 2 with the 99, and then he adds those up. And then 2 plus 99 also gives him a 101. Then he groups together the next two numbers. He puts the 3 with the 98. He also gets 101. And he does this however many times he needs to until all the numbers get underlined. So the question is, how many pairs of numbers can you make from this series? Well, what he noticed was he has 50 pairs because 1 and 100 would be the first pair, 2 and 99 would be the second pair, 3 and 98 would be the third pair, and then it goes on and on and on. And then I've written out some of the terms down here, right? And if I underline the 49 and I put it with the 52, you can add those up to get 101. And then what he does is he puts the 50 with the 51 and he also gets 101. So he did this too. So how many pairs of numbers does he have? he has 50 pairs. 50 pairs. So essentially, he's getting 101 50 times. So he does 101 times 50. Once he multiplies those two numbers, he gets 50/50. So that's the way he was able to do it. So this is what you call an arithmetic series. Arithmetic series. And the reason why it's arithmetic is because the sequence goes up by 1 each time. So to get from 1 to 2, you need to add 1. And to get from 2 to 3, you also need to add 1. And you keep on going until you reach some number, and then you terminate the series at some point, which is 100 right here. So essentially what he's doing is he's taking the lowest number, he's putting it with the highest number, and he's pairing up the numbers that way until he gets 101 50 different times. So that's what an arithmetic series is going to look like. And eventually, we're going to get to geometric series, and we're going to see what that looks like. But essentially, you're just multiplying by a number each time. Okay, so let's talk about sigma notation. So when we talk about sigma notation, we're going to have the Greek letter sigma. So this is going to be a Greek letter. It's actually going to be a capital S. A capital S. And we call that sigma. So what this looks like is, it kind of looks like a capital E, but do know that it's supposed to be a capital S. At least it is in Greek. Now, a lowercase s, which would be this, we actually write that as lowercase sigma, which kind of looks like a baseball cap. But anyways, going back to sigma notation, this is a capital S. And what we're going to do is we're going to have something written on the bottom, and we're going to have something written on the top. So let's start at the bottom. We're going to have an index. The index is going to be denoted by I, a lowercase I. And that I is going to start off being equal to some number, let's say 1. So I is going to start off at 1, and then it's going to increase until it gets to its final number, which we put on top. And let's say the final number is n. We usually stop it at n. Okay, where n is some whole number. So then we have our start on the bottom, we have our stop at the top, and then over here to the right of the sigma, we're going to put our formula. And for now, we're going to use AI. AI. So let's go ahead and label this, and I'll tell you all about it and how we can use it to solve a series question. So like I was saying earlier, let me change my color to gold. This is going to be called the lower limit. This is called the lower limit. And up here, we have the upper limit. So it's going to stop at the upper limit. Now, typically we start at the lower limit. So beside this, I'm going to write start. So we're going to start at I equals 1. And then I'm going to change my color to red. And we're going to stop at the upper limit. So we start off at I equals 1, and we go all the way until I equals n. So we're going to let I be 1 first, and then we're going to let I be 2, then we're going to let I be 3, and then we go so far until we stop at I equals n, and that's where we don't go any further. Okay. And the AI right here, that's going to be the formula, or we call it the argument. The argument. Okay. So what is this going to look like? Well, when we write it all out, what we're going to do is we're going to let I be 1 first. So if I let I be 1, I'm going to get A1. That's the first term of the sequence, right? Plus, now we're going to let I be 2. What happens if I is 2? Well, we get A2, right? That would be the second number in the sequence. Then we're going to let I be 3. We'll see what happens when I is 3. If I is 3, then we get A3. That's the third term in a sequence. And then we write a plus and then a dot, dot, dot until we get to the very end, which is I equals n. So what if I is n? Well, then we would have an, right? And then we stop there. We don't go any further. And that's it. That's our series. So we're basically taking every single number in a sequence and we're adding them all up to see what we get. And we're always stopping at some finite number. We just call it n. Okay? So that is called a partial series. Partial series. Now, the reason why we call it a partial series is because it ends at some point. It ends at some point. For this example, it's going to end at I equals n. So it's going to start at some point and it's going to end at some point. And we call that a partial series or a finite series. And later we'll talk about infinite series and what that would look like. Okay. So this is sigma notation, and we'll be looking at that more in the future. Okay. So let's continue that talk about series. We're going to look at an infinite series. Okay. So when you have an infinite series, that means you have an infinite number of numbers that you're adding up. So what that's going to look like is you're still going to have your capital sigma, and you're still going to have the same argument. You're still going to have AI. It's going to have to start at some point, right? So we're going to start at I equals 1 as usual. But we're not going to stop at n. We're going to put the infinity symbol on the top. So with the infinity symbol, what that's going to look like is we're going to start with I equals 1. So let's let I be 1. Then we're going to add. Okay. Now what if I is 2 instead of 1? Then you would get A2. Now let's let I be 3. You would get A3, the third term in the sequence. And then you would just keep on going, plus dot, dot, dot. And that's an infinite series. An infinite series does not end. It just keeps on going forever. Okay. Now, sometimes you'll see it written like this. You'll see it written as S infinity. S infinity. The S just stands for sum. And if we're writing a partial series, it's going to end at some point. So if we have a partial series, you're going to stop at n, just like we did on the last slide. And when we write that, we write it as Sn. So this is the sum that's going to end at n. And we write this as A1 plus A2 plus A3 plus ... plus an, and we'll end it there. Okay, so that's the difference between a partial series and an infinite series. The infinite series, you're adding up an infinite number of numbers. But for a partial series, which you see on the bottom half of the screen, that's actually going to end at some point. Okay. So that's the difference between partial and infinite. So what we're going to do is we're going to do a couple examples where we're going to plug in for n. Now this time the index, instead of I, it's going to be an n. But don't let that fool you. You always start at the bottom. So we're starting at n equals 1, and we're always going to stop at the top. Whatever number is at the top, we're going to stop there. So we're actually going to be stopping where n is 5. Okay? So let's let n be 1 and see what happens. When we plug in n as 1 right here, we're going to get 1 squared. And that's because I'm just letting n be 1 and seeing what happens after that. Okay? Plus, now we're going to let n be 2 and see what happens. Let's let n be 2. So if n is 2, we're going to get 2 squared. Plus, now let's let n be 3 and see what happens. We're going to get 3 squared. And once again, all I'm doing is I'm plugging in for n. I'm not changing anything else. Plus, let's let n be 4 and see what happens. We get 4 squared. And then the last number we're going to plug in is 5 because we're going to stop here. We get 5 squared. Okay? So now we've plugged in all our numbers, and the last thing we need to do is simplify. Now, I know that 1 squared is just going to be 1 times 1, right? And that's just going to be 1. Over here, 2 squared is going to give me 4. Here, 3 squared is going to give me 9. 4 squared is 16, and 5 squared is 25. So now we're just going to add up all the numbers. So 1 plus 4 is going to give me 5. I'll put that with the 25 to get 30. 9 plus 16, that's going to give me 25. So I'm putting these two terms together. And then 30 plus 25 is going to give me 55. And I'm done. So the answer is 55. Okay, so that's how the partial series works for this example. Now down below it, we have another partial series. This one is actually going to start at 0, but it's still going to end at 4. So I'm going to plug in for I, since I is my index. So if I let I be 0, what happens? I get 0 plus 6. And I'm going to put this in parentheses. You'll see why in a minute. So I get 0 plus 6 for the first one. Just letting I be 0 and seeing what happens. Plus, Okay. Now I'm going to let I be 1 and see what happens. 1 plus 6 plus. Now I'm going to let I be 2 and see what happens. I get 2 plus 6 plus. Okay, now I is going to be 3. I get 3 plus 6. And then the last number I need to plug in is 4 because I'm going to stop at 4. I get 4 plus 6. Okay. So now I plugged in all my numbers, and now all I need to do is simplify. 0 plus 6 is going to give me 6. 1 plus 6 is going to give me 7. 2 plus 6 is going to give me 8. 3 plus 6 is going to give me 9. And 4 plus 6 is going to give me 10. So now I just have 5 numbers that I need to add up. Okay. So what's going to happen here? 6 and 7 are going to give me 13. It's going to give me 13. And 13 plus 8 is going to give me 21. 21 plus 9 is going to give me 30. And then 30 plus 10 is going to give me 40. And then I'm done. Okay, so that's how partial series works. You're just plugging in whatever the index is, right? For the first problem, it was n, so I'm just letting n be 1 first and seeing what happens. And then below here, I see that I is the index. I starts at 0, and it goes all the way to 4, and then it stops. So I'm just plugging in all those numbers for I into whatever my formula is right here, my argument, and then I just go from there pretty much. So those are some examples of where we use sigma and we actually get a number for our answer. All right, so let's talk about some properties of summation. Now, whenever you use summation, you're using that capital sigma letter, and you actually have some rules that you can follow when you're doing summation. So when I'm dealing with a sum, I'm going to have the capital Greek letter sigma. And for all of these examples, I'm going to start with I equals 1, and I'm going to stop at n. So let's say I have in parentheses AI plus BI. AI plus BI. Well, since I have 2 different arguments right here, and I'll underline them in yellow, I can actually break those apart into 2 different sigmas, right? So I can have a sigma right here and a sigma right here. And for this one, I'm going to have AI. For this one, I'm going to have BI. So what I've done is I've taken the parentheses and I've broken it apart into 2 different arguments. I'm adding in the middle, of course. So I'm going to be adding the 2 sigma terms. I'm going to have AI right here and BI over here. And they're both going to start at 1 and they're going to end at n, just like the original did. Okay, so that's the sum law. What would the difference law look like? Well, if I had something like this, could you finish the formula? So let's say I'm starting off with I equals 1 and I'm going all the way to n. And then let's say I have AI minus BI. What would that look like? Well, it would look exactly the same thing as this, right? Except the plus would be a minus this time, since we're subtracting in the middle. But just like before, I have two different arguments right here, AI and BI. So I can actually break those apart into two different sigmas. So I can write this as AI minus BI, where I goes from 1 to n. So that's what sum and difference looks like. You can actually break those apart into two different sigma terms. Okay? Now let's do the constant multiple law. What would that look like? Well, let's say I have the sigma, and like always, it's going from 1 to n, just like before. But this time I have k times ai. So what would that look like? Well, the AI is the same thing as what we've been doing before, right? AI is the argument, but I'm multiplying it by k. And k is a constant. That's why we call it constant multiple. So what that k is going to do is it's going to actually go to the beginning. I'm going to have a k out in front, and I'm going to multiply it by sigma ai, where I goes from 1 to n. So that's the constant multiple law. Whenever you're multiplying by a constant, and right now I want to specify where k is a constant, that constant is going to move from the argument to out in front. And you can also go the other way too. If it starts off in front, you can move it with the argument ai. And that's only if you're multiplying by a number, k. All right. So I'll leave that up there for a little bit so you guys can get that. And then we'll move on to the series formulas. So there's actually going to be two summation formulas that you need to know. They're called the series formulas. There's one for arithmetic sequences, but there's also one for geometric sequences. And you'll see that on the next slide. Okay, so partial series formulas. There are two formulas that you need to know. There's one for arithmetic series, and there's one for geometric series. Now, like before, I told you that we're adding d each time in an arithmetic sequence to get to each number. And in a geometric sequence, we're multiplying by r each time to get to each new number. So the formulas for the arithmetic series is going to be Sn, that's my partial series, and it's going to be n times a1 plus an, all divided by 2. So what you're doing here is you're taking the first number, which is a1, and you're taking the last number, which is an. You're taking the average of the two, so I'm going to add them up and divide by 2. And then at the very end, I'm multiplying by how many numbers there are. There's going to be n numbers in the series. So that's what I'm multiplying by on the outside. I'm multiplying by n on the outside. So that's the arithmetic series. And whenever you have an arithmetic series, you're always going to be using that formula. Okay, so moving on to geometric series, we multiply by r each time to get to every single new number in the sequence. So this formula is going to look like this. We're going to take the first term of the sequence, we're going to put it on the outside, and on the inside of the parentheses, you're going to have 1 minus r to the n power divided by 1 minus r on the bottom. And that's the geometric series. Now notice for this one, you're dividing by 1 minus r, and you never really want to divide by 0. So we're going to add the following stipulation where r cannot be equal to 1. We'll just add that to it. Because what if r was 1? Well, then you'd have 1 minus 1 at the bottom. That's not good. That's going to get you 0. And we don't want to be dividing by 0 at all. So that's the arithmetic series, and that's the geometric series. And I'll leave that up there for a little bit because we're going to go into a couple examples of how we use the formulas on the next slide. Okay, so that's the difference between arithmetic and geometric. Okay, so here I have an arithmetic series. We're adding up all the numbers between 3 and 51. And how does it move each time? Well, to get from 3 to 7, we need to add 4. So plus 4. To get from 7 to 11, we are adding 4. And we're going to add 4 however many times until we get to 51, and then we stop. So because we stop at some number, and in this case it's 51, this is called a partial arithmetic series. And we know it's arithmetic because we're adding 4 each time to get to every single new number. So we're going to use the arithmetic formula to help us with this. And to remind you, the formula is Sn equals n times a1 plus an, where everything is divided by 2. Okay, so we need to figure out what n is. We need to figure out what the first term is and what the last term is. Well, it's pretty easy to figure out what the first term is because we're starting at 3. So that's going to be my first term, my a1. And then my an, that's going to be the last term, which is also pretty easy to figure out. That's going to be 51. And then n is the number of numbers that we have. Now down below, I've already written this series as a formula. What you'll notice is we're going to have 13 numbers. 13 because we're stopping at 13. So let me go down here. I'm going to erase the question mark and we'll start listing out these terms. Okay, so what if I let n be 1 first? Then I'm going to get 4 times 1 minus 1. That's going to give me 3. And then I say, well, what if n is 2? I get 4 times 2, which is 8, minus 1 is 7. And I keep on going until I get to the final number, which is 13. What if n is 13? Then I'll get 4 times 13, which is 52. 52 minus 1 is 51. So we know that we're going to have 13 numbers that we need to add up. So n is going to be 13. And in parentheses, we're going to have the first term, which is 3. We're going to have the last term, which is 51. And we're dividing everything by 2, as the formula says. Okay, so on the inside, I've got 3 plus 51, and I know that that's going to be 54. 54. And we still need to divide by 2. 54 divided by 2, that's going to be 27. 27, yep. And then 13 times 27 is what? Well, working it out, let's see if I can do this real quick. 7 times 3 is 21, carry the 2. 3 times 2 is 6, plus 2 is 8. Placeholder 0. And now I'm multiplying everything by 1. So 1 times 7 is 7. 1 times 2 is 2. And then if I add these up, I get 1, 5, 3. So 351. So if I was to add up all the numbers between 3 and 51, we're increasing by 4 each time, right? We're going to get to 351. So that's what an arithmetic series looks like. You're using the formula, you're trying to figure out how many numbers you have, what your first number is, what your last number is, and you're dividing by 2 at the very end. So 351. We're going to be looking at a geometric series next, which is a little bit more difficult in that it requires more calculation. So let's take a look at that. Okay, geometric series. So this time we have a sequence and we're multiplying by r each time. So to get from 1/27 to 1/9, what are we multiplying by? To get from 1/9 to 1/3, what are we multiplying by? And then what do we multiply by each time? So to get from 1/27 to 1/9, we're going to be multiplying by 3. Notice that we're multiplying by 3 each time. So we're multiplying by 3 to get to 1/3. If we multiply by 3 again, 1/3 times 3 is going to give us 1. 1 times 3 will give us 3. And then we're multiplying by 3 until we get to 243. And then we stop. So I've written the series down here. And this time my argument is 3 to the n minus 4 power. So let's see how this works. So what I'm doing here is we're starting with n equals 1, okay? So what if n is 1? Well, we would have 3 to the 1 minus 4 power. Plus, okay, now what if n is 2? We'll get 3 to the 2 minus 4 power. Okay. Now what if n is 3? We get 3 to the 3 minus 4 power. And this goes on and on and on until we get to n equals 9, which is the final number, and then we stop. So what if n is 9? We'll get 3 to the 9 minus 4. 3 to the 9 minus 4 power. So simplifying this a little bit, 1 minus 4 is going to give us negative 3. 2 minus 4 is going to give us negative 2. 3 minus 4 is going to give us negative 1. And then we're going all the way until we get to 3 to the 5th. And when we do these negative exponents, that's how we get 1/27. 3 to the negative 2 power is going to give us 1/9. 3 to the negative 1 power is going to give us 1/3. And then so on and so forth until we get to 3 to the 5th power. That's going to give us 243. So this series is actually going to work for us. So what was the formula again? The formula for the geometric series, that was Sn equals A1 times 1 minus r to the n over 1 minus r. Okay. So A1 is going to be the first term. That's easy. That's 1/27. So A1 is going to be that first term that we have. And then we're going to have this complicated fraction right here where we have 1 minus r to the n power. What is r? Well, that's going to be 3, since we're multiplying by 3 each time. And what is n? That's the number that we stop at. Since we have 9 numbers, we're stopping at 9. And then in the bottom, we have 1 minus r, which is 1 minus 3. Okay, so now we just need to figure this out, simplify a little bit, and then we'll multiply the 1 over 27 by whatever we get inside the parentheses. So what's 3 to the 9th power? 3 to the 9th power. I'm going to go grab my calculator, and I'll be right back. Okay, 3 to the 9th power, that is, oh boy. Okay, we got 1 over 27. 3 to the 9th power is 19683. And then 1 minus 3 at the bottom is going to give us negative 2. Okay. Good, we got that out of the way. All right. So we still have 1 over 27 on the outside. That hasn't changed. On the inside, I have 1 minus 19683. What would that be? That would be negative 19682 divided by negative 2. Okay, so we're almost there. We just need to simplify a little bit more. So I'm still going to have my 1 over 27 on the outside. On the inside, I'm dividing these two numbers. And when I do divide them, I'm going to get 9841. And then if I multiply 1 over 27 by that, I'm going to get, I think I'm going to get a fraction. Yep. It's actually just going to be the fraction 9841 over 27. So I'll stop right there. This is our answer. And since I can't simplify that down anymore, then I have to stop there. Okay. So does this make sense to you? If I add up all these numbers, I get this number right here. It seems crazy, but with the formula, that's what it says. So that's the geometric series. So you're going to be using that formula to help you out on 3 of the problems in the homework. And the other 3 are going to be arithmetic series. So you're going to be using the arithmetic formula, and then you're going to switch over to using the geometric formula. Okay. And then the last 4 problems on the homework are going to be infinite series. So let's take a look at that. Okay. Infinite geometric series. Okay. Just like before, we're going to have capital S, and we're going to have an infinity symbol. And whenever I have an infinite geometric series, we're basically asking the question, is it possible to add up an infinite number of numbers? And the answer is actually yes, but only if the ratio r is between -1 and 1. So let me show you what I mean by that. So for an infinite series, we're going to have that capital sigma. We're going to start at I equals 1, and we're going to have the infinity symbol on the top. This just tells us the series is infinite. You're adding up an infinite number of numbers, and I'm going to put AI as the argument. So just like before, we're going to let I be 1, we get A1. We're going to let I be 2, we get A2. We're going to let I be 3. We get A3, and then so on. It never ends. Now, to get from the first number to the second number, since it's a geometric series, you need to multiply by r each time. So we need to multiply by r to get to A2. And we need to multiply by r to get to A3. And then we multiply by r an infinite number of times. So here's the formula. We're going to have this equal to A1 on top. And on the bottom, we're dividing by 1 minus r. And that's it. That's the formula. So what does this formula tell you? Well, it tells you that you're putting the first term on top. That's what the A1 means. And then on the bottom, you have 1 minus r, 1 minus that common ratio. So what are you multiplying by each time? It's going to be r, right? So we're going to put 1 minus r on the bottom. And this is where the absolute value of r is less than 1. Or you could also write that as r is going to be between -1 and +1. Okay, so what you really need to know is this formula right here. So we're going to be using that formula on the next slide to solve an infinite series. So let's take a look at it. Okay, so here I have an infinite series, and I'm starting at n equals 1, and I'm going up to infinity. So let's just plug in numbers and see what we get. Now, if I let n be 1, what's going to happen here? I'm going to have 1/2 to the 1 minus 1 power. Plus, okay. Now, what if n equals 2? I'm going to have 1/2 to the 2 minus 1 power. And it just keeps on going like that. Okay, so simplifying a little bit, I know that 1 minus 1 is 0. So I'm going to have 1/2 to the 0 power. Over here, I know that 2 minus 1 is 1. So I'm going to have 1/2 to the first power. And you can see how the pattern is, right? I start at 0, I go to 1, and then I'm probably going to go to 2 after that. But I'm going to put plus ... So can we simplify this a little bit more? We actually can. Remember that anything to the 0 power is 1. So we're going to get 1 right here. And 1/2 to the 1 power, that would just be 1/2. And then the next number you're going to get is 1/4, since you're multiplying by 1/2 each time. So we need to add up an infinite number of numbers. That's what we're doing here. And what's our r value going to be? Well, what are we multiplying by each time? That's going to be what r is. So I'll let you think about that. What are we multiplying by each time? So the formula we're going to use is S infinity equals A1 over 1 minus r. Okay, so A1 is going to be our first number. Whatever the first number is in the sequence, we're going to put that on top. The first number is 1. So we're going to put that on top of the fraction. And on the bottom of the fraction, we're going to have 1 minus r. Well, what is r? That's what we multiply by each time. So what are we multiplying by to get from 1 to 1/2? And to get from 1/2 to 1/4? We're multiplying by 1/2 each time. So we have 1 minus 1/2 on the bottom. Okay. So simplifying this a little bit, the top is going to stay the same. That doesn't change. We still have a 1 on top. What's 1 minus 1/2? That would just give us 1/2. So we have 1 divided by 1/2. That's going to give us 2. So that's going to be our answer, 2. Okay. And I did say that the formula only works if r is between 1 and -1, right? What is our r? Since our r is 1/2, we do know that 1/2 is going to be between -1 and +1. So I can say that 1/2 is less than 1, but it's also greater than -1. So because 1/2 is kind of in between the two limits, we can say that we can actually add up all these numbers and get an answer. Okay. Now I'm going to show you an example of something that would not have an answer. So let's look at the next slide. Okay. So what if I had something like this? What if I had sigma infinity where I equals 1? We'll start off with I equals 1, and we'll just put I right here. So what would this look like? Well, let's plug in numbers and see what we get. Let's start off with I being 1. If I is 1, then we'll just have 1. Then we're going to let I be 2. If I is 2, then we'll just have 2. We let I be 3, we get 3, and so on and so forth. So what would this be? Here, you're adding up an infinite number of numbers. And because we're not multiplying by anything to get from one number to the next, right? There's not really a common ratio that would be the same. Going from 1 to 2, you'd be multiplying by 2, obviously. But here, you'd be multiplying by 1.5. So we don't really have a common ratio for this. So this is not an infinite geometric series. So we can't use that formula that we've been using. If we add up an infinite number of numbers like this, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, and we keep on going, eventually we're going to get to infinity. So we say that this series diverges to positive infinity. Okay. But in the last example, remember that we got 2 for our answer. So we say that this series converges to 2. This series converges to 2.